Right. Welcome to Linear Algebra Tutorial 2. So everybody can see my screen? Yes? Okay. And we are on the 3rd of September. Okay, 2021. All right. Today we'll start with the first question, Tutorial 2, question 1. And then we are given the following matrices. A, which is non-square, and B, which is also non-square, because we do not know what is M and N, but they agree with each other, N and N here, so that we can multiply AB. So AB can, the action of AB or the multiplication of AB can be performed because the sizes agree. And then we are then asked, and we're first then told that B has linearly dependent columns. So what does this fact means? So B has linearly dependent column. The fact means that Bx can be zero vector, even though x is not the zero vector. Now, let's get some notations correct first. The size of B is n by p. Therefore, the size of x is Rp. It has p elements in the vector x. What about here? This is a zero vector. The dimension is n. Okay, so you guys, and therefore this guy and this guy is not the same zero. All right, maybe let's have a concrete example. 1, 2, 3. Let's have a dependent column of B. So if I want to have a dependent column of B, it's very easy. The easiest one I can think of is multiply by 2. So the first column and the second column are dependent. You do not need to copy this down because I will post this in YouTube. Now, let's try multiply by what that is non-zero such that I get 0, 0, 0. Okay, so if I do multiply by the first column by 1 and the second column by minus half, then the answer is correct. Its right hand side is 0, 0, 0. So it's a very strange thing. B multiplied by x, and x is not equals to the zero vector. In here, the zero vector is R2, 2 elements. In here, the zero vector is R3, 3 elements. Okay, so you have to get this shorthand right. All right, so it is obvious why this x produces bx equals to 0. Because dependent column basically means that I can find another guy that will subtract to whatever I have now, and then make the sum 0. Okay. So the question now is, what about AB? Now, let's do the abstract version first, and then we can do the concrete version. Okay. The abstract version is very, very fast. So now let's go back to the red pen. And we say that the abstract version of this answer is Bx equals to 0. X is not equals to 0 because B has dependent column. Second step. Multiply by A on the left-hand side for both guys, left-hand side and the right-hand side. A times the 0 vector is A times 0 equals to 0. Yeah. A times anything, sorry, anything times 0 vector is 0. Okay, so the right hand side remains 0. So the third step, by the associative rule, I can do this. I can put a bracket on AB and call him C. So this x and this x as the same is not equals to 0. Something multiplied by a non-zero vector gives you a 0 vector, implying C has dependent column. Finish. Okay, that's it. So I pause now. Right, now I'll give you a concrete version of this. So I will erase the abstract version now. And then we will still use this B and have a concrete A. Okay, let's have a concrete A equals to 1, 1, 0. 1, 0, 1, 0, 1, 1. So it is obvious that the columns of A are independent. Okay, and now let's multiply with B. And we want to multiply with B. We want to have 1, 2, 3, 2, 4, 6. And then we have A multiplied by B. What do we get? This is A, this is B, and what we get if you multiply. Now, there are many ways to think about matrix multiplication. The very interesting way to think about matrix multiplication is this. Okay, this guy multiplied by this row. Let me find a different color. This guy multiplied by second row. And now the third guy multiplied by the third row to give this value here. So this value is equals to 110 times 1 plus the second 2 times 101 plus 3 times 011. The answer is 3, 4, 5. Okay, you go and figure this out. All right. What about the second column? Okay, let's try the second column now with a different color. How about this guy? So if you follow the argument, it will be 2 multiplied by the first column of A plus 4 multiplied by the second column of A plus 3 multiplied by the third. 2, 4, 6, sorry guys. Zero, 1, 1. And the answer is, actually you don't even need to count because you already see that the second column is 2 times the version of the first column. So answer is actually 6, 8, 10. And why did this double happen? Is because the first column, the second column of B is double the value of the first column of B. Therefore, the answer in C, the second column of C is double the first value of first column of C. Okay. So this is the concrete way. Of course, it's not a proof. Yeah, it is just concretely showing you why this thing happened. Why, when columns of B is dependent, will generate columns of C that will also become dependent. But not only dependent, you can actually see the relationship between the columns of C. Okay, I'll pause now. Okay, we are back. So now again, we are doing tutorial 2, linear algebra, question 2. And here, the question says that A and B are square. B is invertible, meaning that B minus 1 exists. Now, whenever I tell you B minus 1 exists, of course, B must exist. The inverse exists, his inverse also exists, okay? AB is invertible, and AB exists because A is square, B is square. So square matrix by square matrix can be multiplied, so that's okay. But in addition to that, he tells you AB is invertible. So AB minus 1 exists. And he has also tell you that AB exists. All right, so he tells you all this, and then he asks you, is A invertible? So this is asking you, actually, the thing that we are trying to prove here is the product of invertible matrices are invertible. So we are actually trying to prove this, okay, in this question. All right, now let's recap. When we say that when we have said that B and B minus 1 exists, the relationship between B and B minus 1 is this. B multiplied by B minus 1 equals to I. That is post-multiply. We also need pre-multiply. B minus 1 times B must be equals to I. For these two conditions to occur, when these two conditions occur, implying the B minus 1 is the inverse of B. Okay? So actually, here B minus 1 is a placeholder. We have no idea what B minus 1 is. Okay? All right. Now, so let's see what happened. We know that we start with this AB. We know that AB exists. And we are going to call him, let's call him C first, okay? And we are going to post multiply by B minus 1. So this means C times B minus 1. Yeah, I didn't change a thing. And then the second step is I'm going to open up the bracket. The what do you call it? The associative theorem tells me that I can change the order of my multiplication. I can do it this way. B minus 1 on my right hand side, C B minus 1. And now by the invertible matrix theorem, by the theorem of invertible matrix, B times B minus 1 is I. So I am left with A equals to C B minus 1. What is C? C was AB. And is AB invertible? Yes. AB minus 1 exists. What about B minus 1? B minus 1 exists, is inverse B exists. So this guy is also invertible. So we have reached the point. We found out that A is a product of two invertible matrices. And then we are going to apply the theorem. The product of invertible matrix is invertible. And if this is true, then A is invertible. So how do we prove? So the third step is show that product of invertible matrix is invertible. And if we can show this, imply that A is invertible. How do we show Well, actually, this is a hack, yeah, in some sense. We say we have A and B. And here A and B is not the upstairs A and B anymore. Some A, some B. Let A minus 1 exist and B minus 1 exist. We let, okay? And then we now try this. AB multiplied by B minus 1, A minus 1 equals to A, B minus 1, A minus 1 equals to A minus 1 equals to A minus 1 equals to I. Finish. So if we post multiply AB by B minus 1, A minus 1, then we'll reach I. What about the other way around? B minus 1, A minus 1, multiplied by AB. And then we again open up. And now you can obviously see that all the minus 1 and the is inverse x will cancel each other and we get I again. So here we have shown that AB has the inverse B minus 1, A minus 1. And if if B minus 1 and A minus 1 are invertible, then AB will have inverse. And then we are done. Okay, so this is a very interesting and important problem to solve. We always need to show that we always use this fact and solve a lot of problems. Where would you see this in Lay's book? Is page 107. So let me go to Lay's book now. Page 107. So this is Lay 5th edition, page 107. So the first thing you need to know is this guy, the theorem number 6. The inverse of AB is B minus 1, A minus 1. And then he also described the same proof as I did just now. And the important thing is this. The product of invertible matrix is invertible. All right. Now I will pause. Okay, welcome back. So this is tutorial 2, question 3, linear algebra. And here we are given square matrices again. And we are A, B, and X are square. And then A and X are invertible. And this guy, A minus identity times X is invertible. All right, so let's write down all that we know first. A and A minus 1 exists. B we don't know. So B is square, that's all we know. X and X minus 1 exists. A minus identity times X, the invertible thing exists, therefore A minus IX exists. Okay, if I tell you the inverse exists, of course, he must exist. Huh? A minus IX must exist. All right, so we now begin. A minus AX minus 1 equals to X minus 1 B. Okay, so how do I start? No. No, he already tell you the inverse exists. Okay, he has already told you. Therefore, the left-hand side is invertible. If the left-hand side is invertible, then the right-hand side product of the two matrices must be invertible. So now we have figured out B minus 1 axis. So this is the first clue. The left-hand side is an invertible matrix. Therefore, the right-hand side, although it's a product of two matrices, the product of these two matrices, these two matrices must be invertible. So B minus 1 axis. All right. What else? Now, we can, of course, then, because if he is the inverse axis, we can invert him again. So we take the inverse of the left-hand side. If we take the inverse of the left-hand side, we must take the inverse of the right-hand side. So let's try now. So okay. So A minus AX, is it? Oh, typo, I think. Okay. Now, so we do A minus AX. We take the inverse. And of course, this reduces to, okay. What about the right-hand side? That's all. Now, we already figure out that the inverse of a product becomes B minus 1, X minus 1, minus 1. B minus 1, X. So this reduces to B minus 1, X. The left-hand side, A minus AX still. We're going to move all the X to the right-hand side. So we are left with A equals to AX plus B minus 1X. Now we will collect all the X. And now the question is, we want to throw away this guy. But to throw away this guy, we must say, is he invertible? But we are told, right? He is invertible, right? A minus 1 axis from the question. A minus 1 axis here, right? So the left-hand side is invertible. The right-hand side is product of two matrices. We are already told that this guy is invertible. This guy is invertible. Therefore, this guy must be invertible. And the answer comes that I can now multiply by A plus B minus 1 minus 1. He exists. So I can just grab him up. X and then left-hand side. And this guy, of course, reduces to identity. The left-hand side is X. The right-hand side is A plus B minus 1, bracket B minus 1. Finish. Okay, so I will pause now. Okay, so we are back. This is tutorial 2, question 4, linear algebra. And let's begin. We first are told that AX equals to 0 is a homogeneous system with n equations and n unknown. So first is the n linear equation and n unknown is basically telling us that A is a matrix with n row by n column. The n row is for the n linear equation. The n column is for the n unknown. So that's what he's telling us. The word homogeneous means that the right-hand side is the zero vector. So the word homogeneous is saying that the right-hand side normally we are told AX equals to B. But now when we talk about homogeneous, B is the zero vector for homogeneous. And then the zero vector, this zero vector is Rn because we have n equation. So this is the information he told you in the first line. In the second line, actually he should bold this guy and say that this is still the zero vector. It's the trivial solution. So the word solution here means the solution here he's talking about is x. The value of the x vector such that ax is equals to 0. The solution is the vector x. What is the trivial solution? The word trivial solution means that x is equals to the 0 vector. So a times the 0 vector, of course, is equals to the 0 vector. That's obvious to everybody. Anything times the 0 will give you 0 on the right-hand side. So it is called the trivial solution. So in the second line, we reach this point. And now, so this is the first point, and this is the second point given to us. And now the third point is show that AK, what is AK? AK is A times A times A, K of them. So we are product of square matrices. So we can product, right? N times N multiplied by N times N is N times N, and therefore we have A of AK of them. And he want to show that AK times X will also have trivial solution. So what? So he actually going roundabout way, okay? This is a very big round to tell you that okay. So the question is, so 4, you think, okay? Theory, when does AX equals to 0? Under what condition AX equals to 0, X is only the trivial solution? Under what condition? In and you should refer to Lay 5E, page 114, the invertible matrix theorem. Okay, let's see Lay. Page 114. So see, he told you in the invertible matrix theorem, the number D tells you that when the matrix is invertible, AX equals to 0 only has a trivial solution. And when this is true, everything else is true. Or the other way to say is when the first line is true, everything else is true. When the second line is true, everything else is true. So all the statements are either true or false. So we are told this. We must make use of another, what do you call that? We're going to use this, okay? We're going to use this to make a point, but let's try. Okay. We are already told that A has only the trivial solution. Since A has only the trivial solution, A minus 1 exists. So we start with number 5 now. Since AX equals to 0 only has trivial, by the invertible matrix theorem, A minus 1 exists. Now, so to answer your question, do we have to prove this theorem? I don't know. So it depends on your question in the exam, because unless we say assume IMT, invertible matrix theorem, then you can. But if not, you have to prove this point. All right. So So let's jump first. We say A minus 1 exists. How are we going to prove? How to prove AK by X, right? I guess this was the question. AK by X equals to 0 only has trivial. So we prove by contradiction. Contradiction. And how to prove by contradiction? Well, we're going to say AK X equals to 0 and X is not equals to 0. So we say that we have a matrix A times A times A, K times multiplied by X. On the right hand side is 0, but X is not 0, and we don't know what AK is. But it implies that AK, of course, this implies that AK has dependent column and so on and so on. And so on and so on. Right. But we know that A minus 1 exists, right? From the top, we know that. Okay, so we are going to do A minus 1, K of them. Multiply by AK. So if we multiply this on the left-hand side, we must do this on the right-hand side. Multiply by 0. A minus 1 times A minus 1, K of them times the 0 vector, still the 0 vector. Over the left-hand side. A minus 1, K of them multiplied by AK will cancel because they are the inverse of each other. Ix equals to 0. What is I? I is identity. What's the dimension of this identity? Is the n by n, because we are told that A is n by n. So identity times X equals to 0. But our first point was X is not equals to 0, right? That was what we started with. Identity times X not equals to 0 equals to 0 vector. This is a contradiction. Something is wrong. And therefore, implying that our assumption that X is not equals to 0 is false. So X must be 0, implying AK times X equals to 0, implying X must be 0. Okay, so this is the proof for this question in this way. But actually, there are other ways to prove it, of course. Once you realize that A is invertible, then A minus 1 is invertible, you are multiplying invertible matrix by invertible matrix, then the left-hand side is always invertible. You will end up with a invertible. Sorry, A times A is invertible matrix. Sorry, A is invertible. A times A is invertible times invertible. Of course, it's still invertible. A times AK times is still invertible. Since it is invertible by the invertible matrix theorem, then we are still back to this guy. So there are many ways to prove this. I'm just using one of the ways. Okay. Right, I'll pause now. Okay, so back to tutorial 2, Q4B. We are given that AX equals to B is consistent. Any consistent of linear equation. We don't even know the size of A. We don't know the size of X, so it's any. What does consistent means here, guys? The word consistent means here that all the equations agree with each other. Okay, so that's the word consistent here. It means that when we perform row reduction, this is the augmented matrix, and you perform Gaussian elimination, what will you end up with, guys? You'll end up with pivots of pivots. Okay, you might end up with some pivots, some no pivots, some pivots. But what is the important one is that you end up with the zeros at the bottom, such that on the right-hand side, it is also 0. This is the important part. When the system of equation is consistent, after Gaussian elimination, we would end up with the 0 rows for the A and the B, also 0. Why? Okay, let's try this. 1x plus 1y equals to 1. 1x, the second equation I give you, equals to 2. Oh no, the first equation I told you is 1x plus 1y equals 1. Second one is, all right, let's form the augmented matrix. 1, 1, 1. The second guy is 1, 1, 2. Perform Gaussian elimination. Let us see. 1, 1, 1. Second one, 0, 0. Yes. Is it minus 1? Can you see now? So, what does this mean? It means 0x multiplied by 0y equals to minus 1. That's what it means. And therefore, it means also that somewhere along the line, the equations are inconsistent. They don't agree. Okay, so that's what inconsistent means here. All right, so now we have to revise this. Let's come back to our problem itself. Now, we are told that x0 is a solution to ax equals to 0. It means that ax times 0 is the 0, the homogeneous, is ax0. So a times x0 give you the 0 factor. X0 is the solution to the homogeneous equation. So a times x0 gives you nothing in that sense. You can think about it this way. So it's not very exciting, but actually it's very interesting. Okay. Now let's come back. X1 is a fixed solution. Sometimes the word fixed here is also called particular. So you can check the word particular solution. Okay, so let's see it. Ax1 is a particular solution or fixed solution of B. That's given to us. Ax0 is 0. That's also given to us. Let's add the two guys up. Ax1 plus Ax0 equals to B plus 0. We bracket it up. B plus 0 is still B. Therefore, the general solution is of x is equals to x1 plus x0. So this is a very strange thing. You think that for every equation, I will only find one solution, but that's not true. You already know you can, system of linear equations can have 0 solution, one solution, or sometimes called unique solution. One means unique, or infinite solution. Okay, and it's infinite when x0 is not trivial. If x0 is trivial, it means that it is sum of all 0. Then x1 plus all sum of all 0, sum of 0 vector is of course only x1. So that is unique. But when x0 is infinite, then x1 plus an infinite solution, then you have an infinite solution as well. Okay, but let us see in page 46 what Lei is talking about. So he's talking about this. P is the particular solution. In your tutorial is x1. So he's given you 1 point. But ax equals to 0, he gives you a line. A point plus a line give you that blue line. This blue line is the general solution. This P is a particular solution. This black line is the homogeneous solution. Okay, so you have to read this very carefully. All right, that's the geometric interpretation of particular solution, homogeneous solution, and the general solution. Okay, again, I will pause now. All right, so we are now in tutorial 2, 5a. The columns of a square matrix are linearly independent. So by the invertible matrix theorem, when we are told that A is square and the columns are independent, this implies that A inverse exists. So where do we know? Page 114. We have A is invertible because A is square and it has independent columns. The columns of A span Rm, or the columns of A forms a linearly independent set. The proof is here in this few lines of text. Okay, so A minus 1 exists. Second, what about A square? So there's a typo. This is Rn, okay, not R square. He says, does the columns of A square span Rn? Basically, he's also asking you, is A square invertible? So we are back to, is the product of invertible matrix invertible? So how? So first is A square times X. So we want to prove by contradiction. We say A square times X equals to 0 and X is not equals to 0. So we assume, okay, we let A square times X equals to 0 and X is not equals to 0. What this implies is that A square has dependent column. That's what we are saying. Is this true? Later on, by contradiction, we say this is not true. Second is we know that A minus 1 exists by the invertible matrix theorem because we are given A square, the columns are independent by the invertible matrix. This is true. Therefore, we can do A minus 1 on the left-hand side times A square X. Therefore, we are basically multiplying this guy on the left-hand side and the right-hand side. And therefore, A minus 1 times A minus 1 times 0. Anything times 0 is still the 0 factor. A minus 1 times A square, 2A minus 1 times A square. Of course, this reduces to the identity. And we are back to Ix equals to 0. I is the identity. X, we are told, is not equals to 0. So, of course, this is not true. So, implying that this is false. This is false. Only true when X is equals to 0, implying that A square has independent column. Okay. All right. I think we are done here. Okay. I pause now for just a short time. Right. We are done with tutorial 2, Q5B. AB is invertible. A must be invertible. Okay. So what do we do? So AB minus 1 exists. We let C equals to AB minus 1 first. So we have AB multiplied by C. Of course, this is I, it's obvious. But what does that mean? By the associative rule, I change the order of the bracket. This guy is invertible, of course, because he's the identity. C is invertible. Okay, but to get an invertible matrix, we must be product of invertible matrix. Okay, and therefore A must be invertible. A is invertible. Then we have to prove product of invertible matrix is invertible. And then of course you have to do which what I had done in the previous step. All right, I think I'm done here. So you have to do this, okay? It's not that you don't need to do this. You must do this. But this is the idea. Okay, that's it. I'll pause now.